Good afternoon, ladies and gentlemen, and welcome to today's webinar brought to you by Biomass Magazine. My name is Anna Simmet, and I am Managing Editor for Biomass Magazine. It's my great pleasure to be hosting today's webinar, Advancing Biomass as a Drop-in Coal Replacement. As the U.S. and other countries continue to crack down on CO2 emissions, pre-treatment technologies such as torrefaction, hydrothermal carbonization, and steam expulsion will transform biomass fuel into a material more compatible with existing coal infrastructure, and those technologies are drawing more attention than ever before. That said, I'm joined here today by experts who are all working in this space, and they're ready to give you some valuable perspective and updates on progress. Before we get started, I'd like to go over a few housekeeping items. Attendees can submit questions via the GoToWebinar toolbar on the right-hand side of your screen. We ask that you identify the speaker to whom you'd like the question directed, and our team will forward that question to them when they are finished with their presentation. Our presenters might not be able to answer all of your questions, but some will be answered. And additionally, I'll be asking our panelists a handful of questions at the end of the presentations. So if you have a question you'd like everyone on the panel to address, please indicate that when you ask your question. With that, I'm going to hand it over to Biomass Magazine Executive Editor Tim Ports for a few words about today's webinar.
Today's webinar is sponsored by Hearst Boiler. Existing coal power plants can reduce their carbon footprints and actually extend the lifespan of their equipment by introducing renewable fuels into their boilers with few or no modifications. Green thinking companies are now using biofuels to mitigate the impact of their activities on the environment by reducing the emission of greenhouse gases. This can also generate earnings for your company by saving money on energy costs and by the sale of carbon credits. Solutions based on biomass can provide a convenient, cost-effective way to incorporate more renewable energy into your electricity generation mix. Hearst biomass and gasifier boiler systems can strengthen your bottom line by reducing or even eliminating your energy and disposal costs. Utilizing the combustion of renewable fuel sources, Hearst can help provide successful strategies and technology to reduce the operational costs of new or current facilities. This can help you realize substantial ROI when retrofitting existing coal power plants to proven hybrid and biomass solutions. 47 years of experience designing, engineering, and manufacturing solid fuel-fired and biomass boiler systems with over 10,000 installations worldwide has made Hearst the industry's most popular solid fuel-fired boiler. To learn more about Hearst biomass boiler systems and see models and plan views, please visit HearstBoiler.com today. Again, that's HearstBoiler.com today. Thank you. Back to you, Anna.
Thanks, Tim. With that, we'll go ahead and get started. Our first presenter this afternoon is Mr. Bill Strauss with Future Metrics. Bill, thanks for joining us this afternoon, and I'll let you take it away.
Very good. Is the PowerPoint up okay?
Yes, it is.
Excellent. Okay. Good afternoon, everybody. There's quite a few charts, tables, etc. in this slideshow, and I'm going to go through it relatively quickly. So I encourage you all to come back later and view the webinar at a leisurely pace and take a look at some of the details a little more closely. Very quickly, I'll just go through a few slides on Future Metrics. As many of you know, we're a consulting firm in the wood pellet space. A few of our clients are displayed here. We do stuff from project development to feasibility studies, etc. And just a few quick pictures. There's BBI was kind enough to bestow upon me a few years ago the International Excellence in Bioenergy Award, and I'm very proud of that. And we also were integral in a deal that closed a few months ago with the acquisition of New England Wood Pellet by Rentec. Okay, let's get into the details of today's webinar. As we've heard and probably will see, I'm sure, in the following presentations, a lot of the conversations about drop-in coal replacement are biocoal oriented, And essentially, it's biomass that's been put through a process and increases its energy and usually bulk density. We're going to hear a little bit today about torrefaction, steam explosion, and hydrothermal carbonization. I'm going to talk about torrefaction and steam explosion a little bit later in this presentation that I'm doing. I think, as I show, both torrefied and steam exploded pellets actually do make sense for optimizing long distance transportation because of the higher energy and bulk densities. But it's not necessary, and I'm going to actually go through an analysis here because we're talking about drop-in coal replacements, so we're not necessarily talking about black pellets. We're just talking about pellets of any color. And I'm going to make the case that even white pellets make sense in most cases as almost a drop-in coal replacement. So first of all, how's coal burned in a power plant? Well, we're talking about pulverized coal burners. Essentially, the coal is ground into a dust, pneumatically transferred to a burner, and then blown in, and the combustion takes place very rapidly, almost instantaneously. The dust is gone. The fuel is combusted within a second or so of going through the burners. Very efficient, very clean, and very easy to control. This is a shot of a suspension, a wood dust burner, and actually a wood dust burner and a pulverized coal burner are almost identical. In fact, in many ways, they're exactly the same piece of equipment. So the modification of a pulverized coal plant to burn pulverized wood pellets is actually very minor, very small modifications necessary. So is it technologically feasible to convert a pulverized coal plant to a pulverized pellet plant? Well, I think it is, and it's been proven. And it's actually been proven in a big way in the UK. This is a photograph. It's a little bit old now because the 4 storage domes in the lower right there are finished. This is the Drax power station in the UK. It's a 4,000 megawatt power station. There are 6 boiler lines, 6 turbine generator systems. This facility produces about 8% of all the electricity used in England. And they have converted one of their lines already. The second line is coming on as we speak to pure wood pellets from coal. You can see the coal yard, by the way, as well. When they're going to convert 3 out of 4 of the units, they've said for sure, and maybe even a 4th. With the 3 units converted, that's 7.5 million tons per year of wood pellets. This is a shot of one of the lines. In fact, this is Unit 2, which is running on 100% pellets at 650 megawatts. They did not derate the boiler a bit. It's running at almost 39% efficiency and producing the same amount of electricity as it did when it was running on coal. That's just a shot of the steam turbine at the other end of the generator there. So I think this is a rather large proof of concept. There's no question that white pellets, plain old white pellets, in a large pulverized coal power plant work just fine, and that's been proven. So let's kind of step back a little bit and talk a little bit about power generation itself. And there's really 3 broad components that add up to the total cost: the capital cost to build the plant, the fixed and variable O&M, or operations and maintenance costs, and of course the fuel cost. And a lot of people think fuel cost is really important, and they think, my God, pellets are 2.4 times more expensive than coal. How can that work? Well, the fuel cost is not the largest. I'm getting some odd feedback here. The fuel cost is not the largest component of the total cost of generation, right? Because if it were, then wind, solar.
Just 1 second.
Sure. That was weird.
Okay, I think we got it. Sorry for the interaction part. Go ahead.
Okay, great. We were getting some strange sound feedback. So anyway, fuel cost is by far not the largest component. If it were, obviously wind and solar would be free. Nuclear would be rather cheap because nuclear fuel doesn't cost very much. The primary component is the amortized cost of building the generating facility. And here's, coming up in a minute, will be a table that will just have a lot of stuff in it, so I don't expect you guys to absorb it. But the other thing that also matters is capacity factor, right? Capacity factor is essentially how much actual power is produced as a ratio to the theoretical maximum if the plant ran all the time. Wind and solar have actually rather low capacity factors. The wind doesn't always blow, and I don't think the sun ever shines at night. So the amortized capital cost burden on each megawatt hour produced is much higher on wind and solar. Now, I know there's a lot on this slide, so forgive me, but let's concentrate on just a few little bits here. You'll notice I've circled the low capacity factors for land-based wind. This is essentially several different pathways for generating electricity and a breakdown of the analysis of the total cost per generation. And I just want to point out this is at the power station bus bar. This is before the power leaves the power plant, so it doesn't include any distribution costs or any of that stuff. This is just total pure cost of generation. And it's ranked in order of price or cost. So in this particular relationship, natural gas combined cycle is the lowest cost at about $22 a megawatt hour for the electricity, and solar PV is the highest. You'll notice some fuel costs are zero. But look at the column called fixed capital cost per megawatt hour of electricity. That's to the left-hand side of the red square. That's the biggest chunk of the cost of generation, right? And if we take a look down at the bar chart, you'll see that conversion to pulverized coal is actually competitive. It's cheaper than nuclear, wind, offshore wind, and solar PV. But this is not the end of the story. Let's take a look at the pulverized coal power plant fleet in the United States. There's 428 plants greater than 50 megawatts. They're old. The median age is 48 years. 77% of these plants are 35 years and old or older. And I'm going to assume that if a plant is 35 years old or older, it's fully paid for, right? So that is that the original capital cost has been fully depreciated. And by the way, natural gas plants are relatively new, average age 14 years. You can see the distribution in the big chart below there. So natural gas plants still have most natural gas plants have quite a few years left of operation before they've paid off their CapEx. And hydro, although hydro is great stuff, it really is free fuel once again, very green, but we've pretty much exploited all large hydro opportunities in the United States. You'll notice in this chart the peak of capacity installation was back in the 1970s. And really, in the past 10, 15, 20 years, there's been almost no new large hydro because there isn't any place to put it. It's already been exploited. So let's assume that any conversion from coal to wood pellet fuels, old plants. In this case, the CapEx is already paid for, and the only costs are some conversion in fuel handling, the dry fuel storage and handling systems, and that's it. And that's exactly what Drax has seen in their power plant in the UK, is some investment in that dry storage. You saw the domes and the fuel handling systems. And also, we have to remember that some of these older coal plants also are going to have to upgrade their emissions control systems if they're going to continue to operate. So there's a small cost associated with that as well. And if we take a look at that same chart as I showed a few minutes ago, but now you look at the far left column where I have construction or conversion, you'll see pretty small numbers for pulverized coal plant. And actually, hydro is zeroed out because I'm assuming they're fully paid for. Pulverized coal, there's some upgrades to their pollution control, and the 210 is the cost per kilowatt for the dry storage. Look all the way to the right, we're at $24 a megawatt hour for pulverized coal, pulverized wood pellets, I'm sorry, versus pulverized coal, which is actually quite cheap now because we've zeroed out their amortized cost. And if we look at the bar chart, look at this. Conversion to pulverized pellets from coal is very competitive with natural gas combined cycle. In fact, it's, I thought it was the next chart. If I'll go back to this one, I'm sorry. It's $24 a megawatt hour versus, well, in the older price we had. For natural gas, 21.8. That's actually about a penny a kilowatt hour. And this is another large bonus. This one, I think, is something we all need to remember because a lot of the hue and cry about greening up our power system is that it's going to be expensive and it's going to kill jobs. Well, I've just shown that it's not expensive, that we can actually convert older pulverized coal plants and generate electricity at very competitive prices. So we can create electricity at almost the same price as natural gas generated power But look at this. We actually create jobs. The amount of jobs necessary to provision a 500 megawatt power plant, 2,538 for coal, and this is right from the coal industry's data, and 3,481 jobs to provision the same size power plant running on white wood pellets. It's a job creating, and it's also not lower cost. So I think this kind of sums up some of the really great stuff about this. This is a strategy that doesn't need R&D. We don't have to invent new power plants. Doesn't need massive subsidies. In fact, doesn't even need any significant new infrastructure. And the difference in cost, look at that. It's not even a penny per kilowatt hour. It's amazing. So, and by the way, I've included the cost of dry storage and handling. So I think this is an important relationship that we really need to, us in the pellet industry, need to get out there for others to hear about. So just a few more slides. I've got about 8 or 9 more slides to go. And I'm going to shift over to black pellets a little bit because I think we're going to hear a lot more about that coming up, and a lot of the coal drop-in discussion is about black pellets. And by the way, there's a lot of data coming up here in the next few slides, but we just put out a research paper. Actually, I think the next slide has a link to it, so you guys can get the full paper and read the details at your leisure. But the key is that both torrefaction and steam explosion, and I think we'll hear a little more about thermal. Actually, I can't even remember that one. It's a mouthful. Amber will tell us about that. Both result in much higher bulk density, or much higher energy densities, in some cases higher bulk densities as well. This is a logistics advantage, right? You can pack a lot more energy into the same volume. So more tons per unit of volume and more energy per ton, it lowers your delivery cost. But they're also more expensive. So the question is, do these improvements in densities outweigh the increased cost of production? Well, that's the analysis that we just went through. And you can see up in the top paragraph, there's a fairly detailed paper on this at futuremetrics.com. So, and it's free, so please go visit the website and download it as you wish. We're going to look at gigajoules per metric ton. That's pretty much the standard measure in the international markets. And we're going to assume that the buyer, that is the power utility, is willing to pay the same price per gigajoule for any of the 3 types of pellets. That's white, torrefied, or steam exploded. Basically, they're buying energy. And this is pretty much proven by the way the offtake contracts are structured with the utilities in the UK and Europe. They're based on, say, 17 gigajoules per metric ton. If you happen to deliver 18.5, they'll pay more for your pellets because they're buying energy, not tons, although they are buying tons, but they care about how much energy. Based on today's FOB prices out of Savannah, Georgia for a 45,000 metric ton vessel, they're paying $9.14 a gigajoule FOB, and that's the number we're going to work with going forward. So assuming a cost of $17 a ton for a 45,000 ton vessel, and that's based on Argus Biomass data, that's actual shipping from Savannah to Rotterdam. That's about the price. We can see the first box of numbers shows you the shipping cost per ton. Well, the lower the bulk density, the higher the shipping cost, because the ships cube out, as they say. That is, you can fill up the ship before you hit the weight limit of the ship. It doesn't matter if they're white, torrefied, or steam exploded. You're going to fill that ship up before you ever hit the weight limit. So the higher the bulk density, the more you're going to get on. And you can see that the net value, the margin over white pellets for torrefied or steam exploded is about $2.1 million. So as would be expected, the total value of a delivered shipload of higher bulk and energy density fuel is definitely higher. So that is a logistics advantage. This is a good thing. Okay, so what does it cost to produce these pellets? Well, I don't have data on the hydrothermal conversion, but this is the other two, steam exploded and torrefied. The bottom line shows you how much green wood, and this is based on some assumptions, by the way, is necessary to make a ton of pellets. This is all metric tons, incidentally. The reason I've got a circle around the additional wood for steam production or for the torrefaction reactor is that we don't know the answer, particularly for steam exploded, to what additional wood is necessary. And I'll show you a sensitivity analysis of that in just a second here. As I move through this. But we know that some torrefied reactors, the ones we've looked at, in particular TSI system, requiring no external wood once the system's up and running. So I've assumed no external wood also for the steam explosion process. All right, this is a complicated slide, so I come back and look at this later. But essentially, I've taken into account everything's converted to gigajoules and cost per gigajoule, so we're comparing apples to apples all the way across. And I've taken in the additional capital costs, the O&M costs per ton. Wood cost is used because it takes more wood. And eventually, down on the bottom right, you can see the sort of final analysis, and that is the value of delivered pellets and the total cost per gigajoule, and the net value per gigajoule as delivered. And it's greater for torrefied and steam exploded. In fact, this table here shows you the net over the white. So torrefied are about 45 cents a gigajoule better, and steam exploded are about 20 cents a gigajoule or better. This is based on a volume of 60,000 cubic meters, which is about 45,000 tons of steam exploded, which are the highest bulk density. So does this hold up for rail transport? Well, we're going to look at that in a future paper. But typically, rail and trucking is by the ton, not by volume. So that works against improved logistics for black pellets. If it's by volume, you're going to be good. This, quickly, these are a couple sensitivity tables. The top one shows you the relationship of capital cost to whether or not there's a net benefit for these two. The darker shaded cells under 255 is the assumption used in the analysis you just saw. If the additional capital cost per ton goes up to about 290, or not additional, the actual total capital cost per ton per year of installed capacity goes to 290, steam exploded lose their advantage. And the lower one is additional wood necessary to run the reactors or make steam for the steam exploded. The far left column where it's 0, that was the assumption in the model. And you'll see if it's about 0.1 or 0.11 oven dry tons of additional wood necessary, steam exploded loses advantage as well. Once again, all this data is in a paper, so you don't have to try to absorb these rather complex tables. This is a relationship between bulk density and energy density for the two. You can see the sensitivities there as well. Both are in the black, not in the red zone, but it doesn't take too much of a loss of either bulk or energy density to put them in the red zone, which means they've lost their advantage to white pellets. So it's absolutely essential that a maker of black pellets delivers consistently higher density and higher energy dense and higher bulk density material. So can black pellets provide cheaper fuel and work better? Well, I think the answer is yes, a qualified yes. What we don't quantify is hydrophobicity and improved grindability. We know those are potential benefits as well. And we could probably work through that. In fact, we probably will in a future piece of work. The avoided amortized cost of the dry storage handling should give you the value of hydrophobicity and also some advantage to load ships when it's raining or snowing, and the reduction in power generation for grinding. And with that, I will finish up. That, by the way, is a picture of where I live in western Maine. I am done. Hello?
Thank you,
Anybody
Bill.
there? Oh, okay, good. Great.
Appreciate that. Might have a little bit of technical difficulty with Anna. So I'll step in here, and very happy to be able to hand the webinar over to our next speaker, Amber Broke from Desert Research Institute. Amber, go ahead.
Okay, thank you so much for having me. I really appreciate this opportunity to share our work that we've been doing for several years now with our collaborators from GTI and from Parker Towing. And so I'd like to talk to you, although Bill mentioned hydrothermal carbonization, I'm actually going to describe hydrothermal carbonization a little bit, how we can make black pellets or create a coal like fuel from wood. So just a brief outline. Firstly, I'll introduce some of the requirements that a drop-in coal replacement must have and discuss why biomass is not perfectly suited. Then I'll introduce some thermochemical treatment options that can be used to process biomass into a more compatible coal substitute or replacement. And then I'll give you a little bit more detail on the hydrothermal carbonization process and describe some of the work that we're doing in the area, which includes an investigation of the pelletization behaviors and the hydrophobicity from the solids produced by some of these different treatment methods, and then, of course, get to summary and conclusions. So first, what is a drop-in replacement? What do we mean when we say a drop-in replacement? Well, in order to supplant or extend coal use, any substitute really needs to be infrastructure compatible with current practice. So that means with transportation, with handling, and with the use itself for combustion or gasification. So the replacement really should have as similar properties as possible to coal, meaning it should be as energy dense as coal. It should have size and weight that approximates coal, and that's typically in the form of pellets or briquettes, which is how coal is used. It should have good grindability and pulverized like coal, and of course it should be weather resistant for transportation and storage issues. And as these two photos show, coal in both transportation and use can be subject to lots of moisture or weather. And this photo is actually a barge of our collaborator, Parker Towing. And the replacement should be as chemically stable as coal. So, of course, biomass is one possibility. It's also often considered carbon neutral, has the potential to reduce the carbon footprint of these coal power plants. However, it has a lot of challenges with integrating biomass into existing coal infrastructure. So there are handling differences with biomass compared to coal. It's much less energy dense. It often has high moisture content. Woody biomasses are typically, 50% moisture content or so, which results in actual energy contents that are about a third less than that of bituminous coal. So the illustration here on the lower left shows the space requirements for storing equivalent energy contents of woody biomass. So the wood pile is about 3 times larger than the coal pile, which of course has implications for both transportation and storage costs, as Bill just discussed. And so, we can densify biomass through pelletization to reduce the space requirements. However, biomass is fibrous, which results in high pellet mill energy requirements for grinding and chopping, and of course it also needs to be dried. It's also very hydrophilic, so the wood pellets are quite unstable in water. As shown in these other pictures, if you expose a wood pellet to high moisture content or drop it in water, they'll swell or completely disintegrate, which of course could cause problems in transportation and storage environments. So also due to the fibrous nature of biomass, it's difficult to grind, which makes it a little bit more difficult to process with coal, and it also has very different chemical and compositional properties, which make it more difficult to co-fire and make operations a bit more unstable. So in addition, biomass feedstocks can be very diverse, any types of wood or woody biomass, lignocellulosic biomass. So any handling difficulties are further exacerbated by differences in biomass types or seasonal differences that there might be. So as Bill also mentioned, there are some thermochemical processing options that can be applied to densify biomass and produce a drop-in replacement. So these processes produce a product that are more similar to coal, and two methods that I'll discuss are torrefaction and hydrothermal carbonization. So, and I think Hiroshi will talk a little bit more about torrefaction, so I'll just kind of go into a brief description. But both of these really, along with steam explosion, have the ability to rapidly convert different kinds of biomass into a single densified form that have properties that are more similar to coal and even maybe look like coal, as shown in these pictures here. So torrefaction first is a mild pyrolysis process that's typically performed at atmospheric pressure in the absence of oxygen. So that requires a dry feedstock. Typical temperature ranges are from 200 to 300 degrees C with processing times of 10 to 90 minutes. And it produces a solid, friable product with very low moisture content, high increased calorific value between 16 to 22 megajoules per kilogram, which is easily crushed, has good grindability. Usually about 30 to 50% of the solid mass is lost during torrefaction, but much of that mass is the oxygen and hydrogen content with less carbon loss, which results in the energy densification. in a product that is more chemically similar to coal. So as a result, the torrefied chars can combust like coal and co-fire well. And the product has improved water tolerance, doesn't completely disintegrate upon exposure to water like the wood pellet, but as I'll illustrate in a couple slides, it's maybe not as good as some of the HTC products. But it's also very challenging to pelletize due to significant dust generation. And if you've ever seen torrefied biomass, it's really dry and powdery, and that it definitely generates some dust when handling it, which creates explosion hazards, which is definitely a problem in pelleting. So hydrothermal carbonization, or HTC, is a wet thermal processing option in which feedstocks do not first have to be dried. So the biomass, or the wet biomass, is treated in hot compressed water at temperatures ranging from 170 to 290, so similar, maybe a little bit lower temperatures than torrefaction, for 5 to 60 minutes, also probably a little bit shorter than torrefaction. About 50 to 70% of the mass is recovered with also greatly reduced oxygen content, so increased energy content, which can range from 20 to 29 megajoules per kilogram depending on the severity of the treatment, the starting feedstock that's used. And the material is soft, easily crushed. It combusts and gasifies like a low-rink coal, and it also pelletizes and is very hydrophobic, which I'll also show here soon. So we've been doing more of the hydrothermal carbonization process, so in just a little bit more detail, as I mentioned, the wet biomass is treated in hot pressurized liquid water, so it has the reduced energy demands of drying the raw biomass and torrefaction. And then the typical temperatures I mentioned in the previous slide, or maybe a little bit wider range, to actually produce a energy dense solid. I would say the typical temperatures for woody feedstocks actually range from 230 to 275. Although we've applied wider ranges of temperatures, and depending on the feedstock, I show this 200 to 275. And then the reaction times are fairly short, from 5 to 30 minutes. So the main product, of course, that we focused on is the hydrochar, friable hydrochar, which has increased energy content and reduced oxygen to carbon ratios. Usually, this pie chart here shows kind of a mass recovery of the starting feedstock that's treated. Around 50 to 70% is recovered as the solid product, depending, again, on the treatment conditions. Higher temperatures, you'll recuperate less of the solid product. With lower temperatures, you would recover more of the solid product. As high as maybe 10% of the starting mass is converted to gases, which is primarily CO2. And there are also some aqueous products such as sugars, acids, and furfurols that are produced and dissolved in the water. And some water can also be produced as well. So at DRI, which is in Reno, Nevada, Desert Research Institute, if you're not familiar with it, we actually have 3 different batch or semi-continuous process reactors that we've developed here. So our smallest, shown here on the upper right, is a 2-chamber reactor, which allows us to keep the biomass and water in separate chambers so that the water can be heated up and biomass can be dropped in. So it really allows us to have precise control of the reaction time and temperature without subjecting the biomass to long heat up time. So we can have reactions as quick as, say, 30 seconds. But we can only treat maybe 1 to 2 grams of feedstock in this reactor. So our next scaled up version, or intermediate version, is a 2-liter power reactor shown on the bottom right of this slide. In this one, the biomass and water are treated in the reactor and heated up together. So the biomass itself is subject to long heat up times. It allows us to treat a little bit more feedstock, about 100 grams. But this one really, you can see the gas cylinders in the picture on the lower right side. We can purge the cylinder or the reactor with an inert gas first and collect the gases afterwards. So that way we can get an accurate mass balance on how much gas was produced, how much of the aqueous product we can recover, and how much solid product. And then we've also developed a semi-continuous process development unit, which is the picture on the lower left of the slide. in this one, we can process 2 to 3 kilograms of feedstock. So these are all very small scale, bench kind of scale reactions that we look at here. And so here's some results from some of our experimentation that we've completed. And we have explored a range of temperatures on a variety of feedstocks, both woody and herbaceous, which are shown here on this slide about the energy content. So the results shown here are all from 30-minute experiments in our intermediate 2-liter scale reactor, although we have seen very similar behavior from our other 2 scales when comparing on severity, which takes into account the time and the temperature of the reaction. So what we see is that above treatment temperatures of around 230 C, we get a really rapid increase in energy content, and at temperatures above 250 degrees C, we have about a 40% increase in the energy content of some of the woody feedstocks, as shown on the 3 upper lines, the red, the orange, and the yellow, which are Tahoe mix out of the Lake Tahoe Basin up near us in Reno, some loblolly pine from Alabama, and pinyon juniper out of Nevada forests, which is a big problem as an invasive species in Nevada. And then the herbaceous feedstocks that we've treated, rice hulls, corn silver, sugarcane bagasse, don't have quite the energy densification that we see for the woody feedstocks, but there's about a 20 to 30% increase in energy content because of the higher ash fraction really in these herbaceous feedstocks. And rice hulls in particular have a very high ash content, which remains behind in the solid product. So we can also look at this effective HTC temperature on the atomic oxygen to carbon ratio, and I'll just look at this slide briefly. I have another slide here next that shows a little bit more detail in this area. But when we look at the oxygen to carbon ratio, in all cases, regardless of the feedstock, really about half of the oxygen content is removed, which is most of the mass reduction. And so all the atomic ratios of the hydrochars approach about 0.2 above treatment temperatures of 250 C, which is really getting into the realm of kind of our low-grade coals. So I've really been showing you results from our work, from HTC produced, I call them hydrochars. So let's take a look at how those compare to biomass, coal, and other torrefied materials. So we can use this Van Crevelen diagram to compare the chemical nature of these materials. And if you're not familiar with this diagram, it compares the atomic hydrogen to carbon ratio to the atomic oxygen to carbon ratio. And so these regions here indicate typical regions for biomass, peat, lignite, coal, anthracite. And there are a couple examples in biomass. Loblolly we've treated a couple times, so that when you look at the ratios, they're up in the biomass region, and then some other coals you can see down in the coal region. So regions up to the right have low energy density. As they go down close to the origin, they have increased energy density. So we can look at hydrochars from HTC and torrefaction here, and I know there's a lot going on in this slide, but here I'm showing the HTZ results from our work that I've shown in the previous slides for a variety of feedstocks at different treatment temperatures, which are the circles, and then some torrefied data, which is taken from the literature, and the references down here at the bottom. So the triangles are the torrefied data. And so you can see on this slide that the energy densification of the hydrochar really begins to approach that of lignite or coal, while the torrefied materials still are in still have properties that are similar to biomass. And so, these are at a range of treatment conditions. So the HTC hydrochars that are up in the biomass region are at relatively low process conditions, where in the coal region they're at higher temperatures, maybe 275 to 295. So from this figure, you can see that even though torrefaction maybe typically utilizes higher temperatures, the energy densification is not as extreme as it is for the HTC. So we also wanted to look at handling characteristics of the hydrochar, and we've been looking at how well it pelletizes with respect to the other materials. So in our pelletization work, we make individual pellets through this manual pellet press and heated die, and characterize the pellets by measuring the mass density, the energy density, the volumetric energy density, the amount of swelling that occurs when immersed in water, which is kind of a unique approach, and the durability before and after water immersion. So I'll explain these over the next couple of slides. So we look first here at the energy density or the energy content of the material. And shown here, it's all on a dry basis. So the raw material has energy contents around 20, both torrefaction and HTC increase the energy content. And the bar here that I'm showing really represents a range of results from different process conditions. So for the HTC process, the lower energy content is likely from lower temperatures, while the upper range is from higher temperatures. And I should also note that we ourselves haven't torrefied any material. So the torrefied material that I'm presenting here was provided to us by 2 different companies. So the ranges of bars for the torrefied materials represent the variations from those materials themselves and probably different process conditions, but we don't know the specifics on the process conditions of these 2 materials. So after pelletization, we can compare the volumetric energy density, which is based on the calorific value and the measured dimensions of and the mass of the pellet. And you can see from this figure that HTC material compresses a bit more than the torrefied material, which results in an increase in the volumetric energy density up to almost 35 gigajoules per meter cubed, which really, as Bill mentioned, would be beneficial for shipping. So we noticed also that the HTC pellets are quite resilient to exposure to water, so we wanted to quantify that. So we came up with this test to immerse them in water and measure the swelling before and after immersion for 60 minutes in water. So first here we look at just raw materials, and all these are the pellets are produced in a similar manner. And again, the bars represent a range of conditions or measurements. And so when a raw wood pellet is dropped in water, as I mentioned before, it swells, it falls apart almost immediately. The photograph actually shown here is probably a little on the optimistic side, and that typically a pellet would just crumble when you handle it upon removing it from water. The torrefied material definitely improves the resiliency to water, but it does still swell significantly, about 65 to 78% or so, and it becomes very crumbly upon removing it from water. The HTC pellet, on the other hand, swells only a tiny amount and is very solid and durable when it is removed from water. So we also wanted to look at adding the hydrochar from the HTC as a binder in different quantities. So we looked at 10, 20, and 50% blends to see if it could help improve the water tolerance. So if we, of course, dropping these pellets in water is a pretty severe treatment, so they do still swell a fair amount, but adding the hydrochar as a binder does improve the stability of the pellet somewhat for both the raw and the torrefied blends, and the amount of swelling is definitely decreased. So we look here at the pellet durability, which is kind of a standard test in the pellet industry in which pellets are tumbled for a set duration, and the weights are measured before and after tumbling. So here's just a picture of our tumbler that we've used. And so standard for most raw wood pellets is about 98% when they're shipped. And so we also have applied this test before and after water immersion. So the raw wood pellet is pretty close to standard, about 98%. It's very durable in its raw form, but after exposure to water, it really doesn't hold up and can't survive the tumbling test at all. So it's the blue X. The torrefied material produces a pellet that's slightly less durable, actually, than the raw pellet, and I think Bill actually alluded to this in his slides, that there's higher fines generated in shipping, so there's a larger amount of lost from fine generations. And this is, if you've ever seen the torrefied material, it's very dry and powdery, so more of it sloughs off during the tumbling test. So even though it has improved water resistance, it still does not withstand the tumbling test after water immersion. Whereas the hydrochar, on the other hand, makes a very durable pellet and has high durability even before and after water immersion. And even the durability is as good or better as raw wood. So again, we looked at the durability of pellets when HTC is used as a binder. Shown here are 50-50% pellet blends. So the durability of both the raw and the torrefied pellets increases to 99% when blended with hydrochar. And you'll note that the bars are a little bit smaller because less conditions were evaluated, so the range isn't as narrow or as broad. However, in both cases, the pellets still don't hold up well after the tumbling test. But again, that water immersion and tumbling is a pretty severe conditions that not many pellets, except for the hydrochar, actually hold up to. So, and we've also looked at blending the hydrochar with coal, and show here that the coal blended pellets are very stable before and after water immersion. So that's pretty promising for storing and co-firing with coal as well. So finally, conclusions. Both torrefaction and HTC are pretty effective routes for increasing the energy density of woody biomass and creating a homogeneous feedstock, which could be suitable for co-firing with coal. The HTC processing results in really superior chars with improved handling characteristics and water resistance. And in fact, the torrefied materials are so fluffy and dry that they make much less stable pellets and also create explosion hazards during pelletization. Compared to raw wood pellets, the torrefied pellets have improved water tolerance, but they still swell and crumble after water immersion. So the hydrochar pellets really have greatly improved water tolerance. And we've actually seen some of these hydrochar pellets sit in a cup of water for months and months and months on end without falling apart or swelling much more than initially. So they're very stable. Compared to the raw wood and torrefied wood, the hydrochar is also much easier to pelletize and could have reduced energy requirements on pelleting. And it could actually even be used as a binding agent or blended with coal or other biomass directly for pelleting or briquetting, which would be useful for co-firing. Even if you wanted to co-fire the white pellets, you could maybe make gray pellets of the black and white combined. So that's it. Here's my contact information. I'd also like to acknowledge our DOE funding sources and other collaborators and contributors. And here's a list of several publications that we have if you'd like some more specific information. So thank you very much.
Thanks, Amber. Amber actually spoke on a related panel at the International Biomass Conference and Expo back in March. So Amber, thanks for coming back and presenting for us again. Looks like, yeah, you bet. Looks like Donald Fosnach has dialed in from the University of Minnesota. Don, can you hear us?
I can hear you.
Perfect. Are you ready to present, Don?
Yep, I'm just going to get it up now.
Sounds great. Bob will hand it over to you momentarily.
Okay. Okay, are we on?
You're good to go. Just put it in presentation mode.
Oh, I want to
and
thank both Bill and Amber for setting, the overall scene for this, because we have worked on both torrefaction and HTC, or hydrothermal carbonization. It's part of our overall program, and just a little bit before I go into it, our institute is an applied institute of the University of Minnesota, and we're located in Duluth. So we like to try to make systems that actually get close to actual commercialization. You'll see in the end that we're trying to move ourselves in that direction. And my co-investigators are listed here. They've done the bulk of the work and are still working very heavily in this area. So what I'd like to talk about really goes into not only the torrefied biomass, but combinations that you'll see with HTC. So the reason why we're working on this in northeast Minnesota is that we've lost a lot of resource use going into more traditional uses, either in paper or in strand board plants. And so we actually have a significant excess of potentially harvestable wood up here in Minnesota. And that's led to more potential for wildfires, loss of logging opportunities, and really points the direction of trying to use that wood for other purposes. And so we've looked at it from a couple different standpoints. One is the use in boiler operations like a power plant or in a distributed power type system. And to do that without much capital change, as Bill has alluded to, it'd be nice to make the biomass as coal-like as possible so that you had very little change in capital at the existing power plants. We've also found that biomass pretreatment makes it much more easily gasified for subsequent conversion of that gas to a liquid fuel, because you take certain things out that really cause you some difficulties in making a good producer gas. So we've concentrated on pre-treating the biomass in 2 different ways, and I'm going to walk you through that today. So torrefaction, I think, has already been discussed. I'll just review it. It's somewhat akin to coffee roasting, that you can get a light roast to a dark roast, and depending upon the treatment temperature, you can change the color of that biomass, increase the energy density, but at the same time, you start tearing apart the structure of the biomass, and it becomes more difficult then to bind together. So there's an optimum in terms of trying to get the right energy value as well as some other properties which we think are very important. And there's a number of different reactor types out there, ranging from vibrating beds, fixed beds, microwave treatments, rotary kilns, fluid beds, toroidal beds, and moving beds, which could be used for doing this type of thing. And usually most systems will have a dryer associated with the torrefier, and then a way to put the energy in through combustion of either the volatile matter that's basically generated during the torrefaction process, or using some of the wood that might be burnt just to produce energy. As far as what we've done, we've gone through various stages of torrefaction, ranging from gram scale with an oven that's somewhat akin to a thermogravimetric analysis type device, to a larger scale where we can make hundreds of grams, to a gas-fired kiln. We also call this our pig roaster. It can be used for multi-purposes. And then more sophisticatedly, we put together a pilot scale rotary kiln that's electrically heated through contact electric heating elements. And all of this is indirectly heated so that we don't allow the air to get in there while we're doing the torrefaction reaction. And we have now obtained this Hale and Patterson indirectly fired kiln, which will be implemented by fall to produce a tonnage level material from our facilities. So we did this in various stages. The benchtop work really went on from about 2007 to 2009. That we were able to establish heating values from the different products, look at grind specification, look at density and pressure profiles in trying to densify materials. And we moved from there to this larger pilot unit, where we started looking at producing wood coal replacements at different levels, looking at emissions profiles coming from coal with torrefied biomass, and then we're hopefully getting into actual plant demonstration in conjunction with major power companies to have enough material so that they can really understand what the overall benefits will be in terms of both use as a coal substitute and then environmental consequences of doing that. So we're putting together a big system in conjunction with a couple cooperators, Hale and Patterson for the kiln, and MEC providing the dryer that will go with that kiln. And I'll talk a little bit more about that. The other thing we found is that depending upon the end user, they may want to have the final product in different forms. So we've investigated various techniques ranging from briquetting to pelleting to ram briquetting. Each one has a certain property associated with it that you have to match with the material properties. And it's not straightforward in many cases to result in a well-defined densible product. This just shows you some of that. We've done a lot of work on heated die systems. We have a lab briquetter. We have a rotary briquetter that can make tonnage quantities. We also have a reciprocating ram machine, which is very interesting in that this can produce a lot of extrudates. And then we're adding capabilities from 2 other cooperators. One's from Federal Machine, it's compacto, it makes finger-like material. And then a specialty machine from Amity Technology out of Fargo. This shows you some other capabilities. We do have a conventional pellet mill as well as a lab pellet mill and various extruders and spiritizers that we've used over the course of the last 7 years. As far as characterization, very similar to the Desert Research Institute, we have various devices to characterize things, ranging from calorific value to looking at the gasification properties of the biomass, looking at analytical capabilities in terms of carbon and other quantities of material that might be in there, going back and looking at tumble testing and then crushing materials and actually looking at adhesive values of materials and try to pull them apart. So this basically shows you on the bottom here, depending upon the degree of torrefaction, you can get a very light colored material, similar, like I say, with coffee roasting, to a very dark coal-like color. And depending upon what you ultimately want to do with that material, if, for example, if you want to have a little bit more lignin in there to help with the binding properties, you may control your roasting to get you what you need in terms of that. And this is on a dry ash-free basis. You can see that as far as high-growth grindability, the hydrothermally treated materials as well as the torrefied materials actually have good hard-growth grindability numbers, which lowers the grinding energy in the grinding process relative to just woody pellets. So if we look at the basics for torrefaction, the key here is not to over-torrefy. You have to look at what you want in terms of energy, grindability, and yield targets and binding capability simultaneously. So we're trying to optimize the temperature, the grindability factors in this compaction regime across the different biomass types. And you really have to mate these things together to get the right torrefaction specification for the end user. So what you do is you basically look at the major macro components of your biomass, and you're taking a lot of that hemicellulose and breaking it down, and you're balancing what happens with these other components in the end by controlling your processing conditions. We've treated a variety of materials, and I've just listed all of them here. All these things can be torrefied. Some are easier to torrefy than others in terms of the process rigor that you have, but basically all these materials can be treated. And you can make strong, durable pellets or briquettes with engineered properties, but you have to also look at other things. And I think Amber has already highlighted some of the things associated with just torrefied wood by itself. You can get into materials that will break down pretty easily if you tumble them or if they're subjected to water immersion. And so we monitor the properties of these different materials coming out after processing. And we just show on this here, you'd like to be able to resist the penetration of water droplets. And for example, if you store these things outside and all they have is a minor amount of rain that hits them, that's one thing. But if you have water that substantially builds up on the bottom, you cause the swelling, as was shown with Amber's results. So we've done various things. We are very similar to Amber. We've looked at properties such as the internal bond strength. We've pulled things apart by looking at how strong the adhesion is. We look at what happens when you soak this stuff, very similar to what Amber's already shown. And we've also subjected it to simulated weather conditions, going back and forth, looking then at the durability of what results from that particular treatment after they're dropped for a number of drops. And this just shows you a couple things. It's a fairly busy graph, but it's an interesting one from the standpoint that the amount of force needed to form a agglomerate using the hydrothermal treated biocoal is much less. So that's the 35,000 kPa at the top versus what you need for torrefied material. So having the HTC product actually allows you to have some pretty good benefits that Amber's already discussed. There is a very easy process for densification associated with the HTC product relative to the torrefied material. At the same time, they have about the same energy density, although you can see, again, as far as specific gravity, the material densifies a little bit further on the HTC side. So we've looked at that in terms of also the internal bond strength, and the HTC product by far has a real good adhesion of the materials together relative to some of the torrefied material. So our process is probably similar to what she showed as the second stage of the development. They have worked at the Desert Research Institute there. We load the materials into a autoclave. We then process that. The processed material ends up as somewhat of a mud. We can then centrifuge that and then separate the liquid and the biocoal, and that then easily agglomerates using a briquetting machine. So if we look at properties, the basic conditions for hydrothermal carbonization, very similar type of situation as already has been cited. Good energy densities result in terms of the final products, and we did not go as high as I think that you cited. I think Amber about 290 degrees. We more or less try to keep it between somewhat on the 230 to 250 level for processing through the HTC process, in contrast to maybe 275 to 300 degrees C for torrefied material. So if you look at hydrothermal carbonization, as Amber found, densification challenges really aren't existent. You can densify the materials even at 20 to 30% moisture and very low pressure. You can actually do post-drying without a dryer by just taking advantage of ambient conditions in some places, probably down in Arizona, for example, that would be good, or in West Africa where it's very dry. The materials are all handleable. Very little water makeup is needed because you bring in the materials in their water holding condition. Bonding conditions are very, very good, better than torrefied materials. And what we have started to look at is blending the HTC technology platform with torrefaction, because we think torrefaction can process things faster in bulk, but HTC would provide a very good material to blend with the torrefied material so that we can get the properties that are optimum in the overall system. And so like torrefaction, we've processed a variety of materials through our HTC area, and we think herbaceous materials especially are very applicable with the HTC process. Just to give you an idea of what kind of changes you get in density in terms of processing, this looks at some cattail material that we processed through the reactor, and we started with a material about this size, and you end up with that much in terms of output, and it gives you the same sort of view, just to give you a perspective. 3 bags of energy product from all those different bales of hay, for example. So hybrid combinations, we've done very similar work as was reported by Amber in binding with coal. It works very well. And we've also done that with using it as a binder for woody pellets, as well as looking at the torrefied biomass. And that has led us to a scheme which we think could be very practical, and that's to have a smaller HTC system with a bigger torrefaction system to allow you to have ease of densification and final product development that will then allow you to have very good shippable products for end users. And this is our scheme that we're working on now. We basically, I'm going to show a picture shortly, we're trying to put this overall system together for demonstration purposes. What we have found is that a lot of people would like to use either torrefied or HTC products, but there's not enough producers out there that can make the quantity they need to actually evaluate it in their power plants or in their potential gasifiers. So we're trying to put together systems that allow that to happen, and this just shows you an overview of that process. We have the MEC dryer now constructed. It's not shipped yet. H&P kiln is on our property now. And we're also putting together a systematic continuous HTC system at the pilot level. This one shows a little bit larger unit that we're also working to design, but in consequence, we basically have a couple reactors probably akin to what was shown by Amber, and then ways to basically take the liquid out, recycle it from a hot water system to preheat, for example, into the final reactor we would have here, and then separating it with a centrifuge at the end to produce the product. So our facility that we're trying to put together is right in the midst of construction right now. The first thing we had to do was take a building that was built in, I think, 1906 and get it up to the conditions necessary for putting all our different reactors in this building. And so a lot of that work has already been done. We had to take off lead paint and asbestos and condition the building, and now that's largely done. We have the H&P kiln on site. The MEC dryer is now built and ready for shipment. We're right in the midst of material handling system and gas handling system design. All densification and product handling details are in engineering, and we have 5 different densification pieces of equipment that we'll use for this. And then later on, we're also going to be putting in a moving bed torrefaction system, which is now under pilot study. And we will have also an advanced boiler generator system being designed where we're going to directly demonstrate the use of the torrefied material to generate electricity. And we're going to be developing that HTC continuous pilot plant, and that will be under design and construction and placed in the same building. So that's the story from here. I think it shows again that materials of a high energy density can be made from a variety of materials, and if you have any questions, we'd be pleased to address those. Thank you.
Thanks very much, Don. A nice presentation, some great photos in there. With that, we'll move on to our final speaker of the day, which is Hiroshi Morihara with HM3 Energy. Hiroshi, if you're ready, the floor is yours.
Yes. Good afternoon. My name is Hiroshi Morihara. I am president of HM3 Energy. I'd like to talk about torrefaction based on our experience in the past 5+ years. People are concerned about availability of biomass in the USA, and according to the Oak Ridge National Lab, they did a billion-ton study and updated in August in 2011. And in the base case, biomass availability maybe was 400 million tons in 2012. It'll go up to over 1 billion tons by 2030. Most of that increase will be energy crops. Briefly, torrefaction is not making biochar, somewhere between char and raw wood. So if you see torrefied material, you see chocolate color. And torrefaction is actually very simple in principle because it's just like roasting coffee beans, and we do it at 240 to 300 degrees C without air, and between a few minutes and maybe 1 hour. In our case, we adjust the temperature so that we can have a residence time of maybe 15 minutes. In case of add residues, in some cases, torrefaction temperature may be much lower. It could be
Hiroshi, I'm sorry to interrupt you.
Yes.
It's a little bit difficult to hear you. Could you try to speak up just a little bit?
Okay. Can you hear better?
That's much better. Thank you.
In case of ag residue, torrefaction temperature may be lower to 15, 20 degrees Celsius. But when you do it properly, it will become brittle. And also, if you have a proper densification, you can dip in water for a day, and it will doesn't crumble like a traditional wood. Now, benefit of certified biomass as wrapping fuel. Our certified biomass, we call it TOR-B, and I'll use that as an example. There's no plant modification necessary to use TOR-B. In fact, we did test burn at the small coal boiler in the Western Research Institute, and they mixed 10% of TOR-B in coal, and then 50%, and then eventually 100% TOR-B and burned in the coal boiler, and it burned beautifully. So you can replace coal without any modification. And unlike Amber's statement, you can make it water resistant. So you can ship on the open hop rail car, and you can store outdoors. And of course, if you do properly, it will be brittle, so you can carbonize the coal. And energy density is very similar to most of the coal used in power generation in this country, which is Powder River Basin coal. It's about 10,000 BTU per pound. But the Powder River Basin coal has about 25% moisture. So you have to boil that one off before the energy can be used. So the net energy-wise, TOR-B may have 20% more energy density than PRB coal. In comparison with raw wood pellets, FOB price factory may be very similar. The difference is that TOR-B has at least 25 more energy density than raw pellets, so shipping costs will be much, much less. Now, important variables in densification, depending on the biomass, lignin content changes, and more lignin the better. And the desired purification condition, I say medium roast, and what it is you want to roast just enough so that the material becomes brittle, but preserving lignin. And when you do that, then OH groups are substituted by unsaturated non-polar group during purification, so that purified particles become hydrophobic. Now that doesn't mean pellet will be hydrophobic, because lignin is the glue to produce pellets. And so what you need is to make it work, particle size must be fairly small, less than 5 millimeters. And lignin needs water to become a glue, so 5 to 5%, 12% water. And the lignin will act at a higher temperature than room temperature, maybe 120 to 150 degrees Celsius. So you want that temperature as a die temperature. And of course, you need pressure, maybe over 1,000 psi. And we use 2 to 3,000 psi. If you do it properly, then you don't need any binders. And oftentimes we say, okay, purification, densification is easy, and there were many, many companies who entered into this business, and they said all you have to do is roast the biomass and then buy a pelletizing pellet, and you get a hydrophobic product. And that's farther from the truth. What it is lignin requires water and a certain amount of temperature. And most importantly, lignin reacts slowly when you make it into glue to make it hydrophobic briquettes. That duration is normally absent from pelletizing. And so many companies have failed in that regard. Another problem is purified biomass is abrasive. So if you try to pelletize and run it for any length of time, dye can be overheated, and the moisture in the pellet becomes steam and pop out of the pelletizer dye, or cause fire, or plug up the dye. So you have all kinds of problems, and some companies use lubricants to keep the dye temperature in control. And so the lubricants is needed to keep the dye temperature control, and some people need the binders to make sure you have enough glue to keep the pellet water resistant. And the binders may be lignin, glycerin, plastics, molasses, paraffin, and I just heard HTC. Those may work as a binder. But
Hey,
our
Hiroshi.
product, yes.
Hiroshi, I apologize. I'm interrupting one more time. It sounds like maybe you're speaking a little too close to the headset or something. There's just a little bit of feedback that we're getting.
Can you do it better now?
Yes, that's better now. If you just speak a little bit louder and just like that, it'll be perfect.
Okay. Let's do a cost comparison between purified and raw pellets. Feedstock, most of raw pellets, they use clean wood, sawdust or chips. We use forest slash. So forest slash is, of course, cheaper. Grinding, pellet require finer grind. In case of our product, we use coarse grind before torrefaction. And once you do torrefaction, then you can use fine grind without much energy. Now, torrefaction is an expense, but torrefaction is a very important process in saving energy in that when you torrefy, biomass, part of the biomass will gasify, and mostly hemicellulose will gasify and produce water and volatile organic compounds. And you normally have 10% energy and you lose 30% mass. The product is more energy density than regular wood, and that 10% energy is used to dry incoming feedstock and also use energy for torrefaction. Now, densification, on the most part, the price will be very similar. Energy content-wise, raw pellet may be 7,000 to 7,500 BTU per pound. Our product may be 10,000 BTU per pound, or 22 to 23 gigajoules per ton, long ton. Storage-wise, raw pellet require silos, and pellet FOB does not require, so there's a big difference in cost. And FOB factory price per unit energy may be very similar between the two. But the delivered cost, purified biomass has an advantage due to difference in energy content and also hydrophobicity. Let's look at the shipping and storage cost comparison between raw pellet and the purified pellet. Raw pellet may contain 17 gigajoules per ton. For that same energy, FOB require only 0.74 tons. So if you ship that amount across the Pacific Ocean to Asia, now first it will go to North American port. Raw pellet require silo, and FOB does not require silo. So there's a difference in storage and handling fee of $18 versus $6. Ocean shipping, difference in weight makes a difference in cost, $35 versus $26. And once you reach the Asian port, you have a similar issue with the storage, so $18 versus $6. And local transportation, $7 versus $5. When you reach the power plant, you have to have a silo to store raw pellets, $8. And in case of 4B, nothing new is necessary, just like coal. And when you feed it into the power plant, because grinding into pulverized material is very expensive with raw pellets, or almost impossible. So you have to have a new seeding system. Oftentimes it may cost $100 million for 300 megawatts. So it may be $7 versus 0. So you add all that cost together, then raw pellet price is $93 for handling and shipping. Soybean cost maybe only $43. So there's a big difference in cost. HM3, our mission is to meet the global need for renewable, economic, and environmentally friendly fuel replacement for coal-fired power. We started as ethanol production using woody biomass in 2008. We quickly switched to solid fuel in 2009. We have experienced leadership and also engineers. We have PhD chemists, PhD chemical engineers, and metallurgical engineers, PhD mechanical engineers. And so together, we've been together all this time. We have talent in various areas, and all of us have worked in the big companies, so we know how to manage better. So what we are doing now is that we come to a point where we are ready to build the biomass extraction densification testing facility. We have gotten grants in the past. We have USDA, SBIR Phase 1 and Phase 2. We got a small low-interest loan from U.S. Endowment for Forestry and Community. And also, we just got a USDA SBIR grant. And we have a sponsor who is paying for this densification testing facility. And this facility will be built in Troutdale, Oregon, and it will have 500 pounds per hour purifier and 5 tons per hour densifier. There's a difference in volume, but this purifier is small, but it's a commercial design. We can scale up to a larger size. And this facility will be completed in spring of 2015. And this facility is open to companies who are serious about licensed out technology, manufacturing or densification technologies. And the companies can bring their raw material or purified material, and we can do the purification or densification in front of their eyes. And key is providing purification densification technologies for licensing worldwide to meet the tremendous demand for second-generation biomass utilization as drop-in replacement fuel for coal. Because the key is that industry hasn't developed very much because each company is very secretive about their technology. So each company may have different processes, different qualities, and so that there is no uniformity. And utilities don't like to have this type of industry and commit long-term contracts. So what we have to do is we have to collaborate and utilize the best purification technologies, and so that we have a constant quality product. And we like to have as many companies as possible producing this product. That's why we like to open up our technology to anybody who are interested. And in making sure that quality is constant, International Energy Association has a committee who is working on this product qualification quality system, and so that we will know what to meet. So that will help unify and make the product consistent. That's all I have. Thank you.
Thanks very much, Hiroshi. We're running right up against 3:30, so we only have time for a couple of questions here. I'll just jump right on into that. This first is an open question to any of the panelists, so panelists feel free to just chime in. It comes from Andy Cronin from BioGreen Tech Ltd, and he asks, white pellets produce a large amount of dust when transferred from ship to train. Is this the case with black pellets?
I can. This is Bill Strauss. Can anybody? Am I on? Can I be heard?
We can hear you, Bill.
Okay. Yeah. Yes. Actually, steam exploded pellets are very low dust. And in the analysis I did, there was I didn't get a chance to point it out, but there's an adjustment for fines or for losses. So black torrefied pellets and white pellets are, I'm just assuming, around 2%. It's 1 to 2% losses typically in transport, sometimes larger. Steam exploded pellets seem to have much better characteristics in terms of low dust creation, and I don't know about hydrothermal carbonization.
This is Amber. Let me just jump in and say that the hydrothermal carbonization is probably right along those lines of the steam exploded, with very low, less than 1% of fines generated, so maybe even, slightly better than the raw wood pellets.
Thanks, Amber and Bill. We have time for one more question. This comes from Paul Iverson, and he asks all panelists, anyone who can answer it, what are your thoughts on 100% conversion versus blending with coal?
Well, I'll start. It works just fine. Co-firing is very common in plants in Europe. And actually in South Korea. South Korea this year will probably import 200 to 400,000 tons of white wood pellets, mostly from the West Coast, although a few shipments have gone from the Georgia or from the Gulf states. They're built there, co-firing.
That's very good. We actually tested some white equivalent pellets at a power plant in the Duluth area, and even at 30% addition, you can see dramatic changes in environmental footprint. So it really depends upon the local optimization of total cost going into the system that might use either the black or white pellets.
Yeah, and I might add that all these exports, I mean, literally many millions of tons a year of pellets are being exported out of North America, somewhere around 5 or 6 million tons this year. Are going to places that have carbon mitigation policies that make coal either more expensive, or there are subsidies provided for replacing coal. We don't have that in the U.S.
Thanks, Bill. And that'll conclude today's call. We received a very high volume of questions, so I'm sure if you contact our panelists following the webinar, they would be happy to answer any outstanding questions you might have. Before I let everyone go, I'd like to once again thank our speakers, Bill, Hiroshi, Donald, and Amber. And of course, a special thank you to our sponsor, Hearst Boiler. And just a reminder, those of you who attended the webinar today qualify for a $250 discount to the National Advanced Biofuel Conference and Expo. That's being held in Minneapolis, October 13th and 14th. Using promo code WEBINAR, you can register at www.advancedbiofuelsconference.com. And last, be sure to check out Biodiesel Magazine's next free webinar installment. It's being held August 28th, and that's titled Biodiesel Technology, Enhancing Profit Through New Processing Technologies. And that'll wrap it up. Have a wonderful afternoon, ladies and gentlemen, and thanks for tuning in.
Bye.